Hi, welcome to chapter 5. We were dealing with antiderivatives. So up until this point, we were taking the derivative, which we hopefully know all the rules by now. This is going backwards. So you kind of have to, I think of it as meta thinking, think a couple steps ahead to get to the final answer. We do have some tricks, but and you can memorize the rules as well, but you almost have to just, like I said, think about it backwards. So the first piece is we're just going to find the derivative. So a couple simple functions here, f of x and g of x. So what's the derivative of f of x? Well, we know how to do this. You bring your 3 in front. I get 3x subtract 1 squared. And the derivative of the constant is just 0. There's a point to this, I swear. Find the derivative of g of x. Same idea to start, bring the 3 in front, x squared, and then the derivative of the constant is 0. So you'll notice that for f prime and g prime, they're the same function, but their original functions were not the same. So when we take an antiderivative in this section, and then later on we'll tweak it to some cases where we don't, we always have to consider, well, there could have been a constant that we don't know about or that we don't know anything about. So if I take my f prime up here and I want to find the antiderivative, go backwards. Well, we say, and we usually use the capital F in this case. That's going to equal, okay, so we know our original function was x cubed. So, add 1, divide. Plus, well, if we're just given, I'm trying to cover it with my hand and you can't see that. If we're just given this, we have no idea what that constant could have been. So we just say plus C for constant. And you don't have to say that C is the constant. It's understood here. I've also been doing way too much of my own math that I had to say. I have to define what all of my variables are. So if we want to take the antiderivative of our g prime, same thing, x cubed plus c. So don't forget the c. You will get dinged on homework if you forget that. It's a frustrating thing to get dinged about because, it's so minimal in the solving of it, but it's important in the end. There are cases where we can solve for the c, and that is coming later in the section. And there's cases where the C isn't going to matter. And I want to say that's 5.3 or 5.4. It's not in the first two sections because I wrote notes about those. Okay. So if we want to define the antiderivative, it's a function f is the antiderivative of little f, when for every x in the domain of little f prime of x equals f of x. Makes way more sense when you read it to yourself and not out loud. Antiderivative. Just go backwards. Okay. For integrals, we're going to deal with two types. There's a couple more out there, but the ones we're going to deal with, especially early game, are indefinite and definite integrals. So indefinite is the section, definite will be 5.3 or 5.4. So you're indefinite, there's no little numbers here, no values here or here. Your definite integrals will have those, and we'll talk about what they mean. So it really just means find the antiderivative. You need the little dx over here because that tells you what variable you're using to find the antiderivative. So if you go on in calc, we could have multiple integrals and you want to differentiate with respect to x first and then y and then z, or change the order. But the order you do that matters. So for us, it doesn't seem to matter, but we want to make good habits if we go on. So we always want that dx. It helps us. And again, definite integrals we will talk more about later. They're honestly one extra step from definite or from indefinite, so they're really not harder. They're just a little bit different. All right, our basic integration rules. Hang on, let me take a drink. I talk too fast, I know. Okay, So let your K, N, and C be real numbers. They're going to be constants most of the time. The constant rule, if we take the derivative of some constant value, the antiderivative, sorry, we get that constant K times X plus some other constant. So if you think about it, go through and on the right side, take the derivative and notice that you'll get back to the left side. If you have a constant multiple of a function, you can just bring that dude out and take the antiderivative. Sum and difference work exactly like you want it to work. So if you have like x squared plus x, you can separate those and do them both separately. And the power rule is the big one we're using right now. So this one says if we have an n, some constant n, and we want to take the antiderivative, well, we add 1 to that value and divide by that new value. If you think about it, take the derivative of a x to a power, how do you do that? You're doing the exact opposite of that. So, sorry, got an alert. Yeah, the big thing to remember on this last one, and that's the one we're going to use the most, to be honest, is divide by the new value for your exponent, not the old one. I used to get dinged with that sometimes. And as always, you add constant c at the end. So, hey, let's do a couple of these. All right, so 3x. We can write this as 3 integral x dx. To be honest, I'm not going to do that ever again, or very rarely. You really don't need to as you go with these. So, all right, my exponent is 1, so I take x, 1 plus 1 is 2, divide it by 1 over that exponent, which is 2, plus c. I almost forgot that. I used to get dinged a lot for that. Okay, that is messy, and I don't like it, so I'm going to clean it up a little bit. Combine my constants, 3 halves, x squared plus c. It's a nice check to mentally take the derivative of that. So if I do take the derivative, the 2's cancel, I get 3x, which is what we should have gotten. You don't have to formally do that, but if you're unsure, try it out, see. Another weird thing about integrals is there can be more than one function that will give you that. Actually, we've already seen that. So you and your friend may do the same problem and come up with 2 different answers, and they're both right. These early sections less so, but as you go on, the functions get a little more complicated, a little weirder, and that happens. I'll bring up my next 3. I have a lot of functions today. All right, this next one, I'm going to rewrite this. Actually, the next 2 I'm going to rewrite. So this is going to turn into, remember, we can bring this up and make it negative. Okay, now we do the same thing. So -3 plus 1, not -1, plus 1 times 1 over -3 plus 1 is -2. Plus my constant. I realize it's backwards as to how I wrote it above, but I like it better this way. Okay. So be careful of adding and subtracting when you have negative numbers. It's easy to goof that up. I usually put my fraction after, just so I know where I'm going with that. You don't have to, just to clean up stage. All right, the next problem, we're again going to rewrite this. Okay. So always rewrite them so you have an exponent on the numerator, sort of thing. All right, I add 1. So that's 3 halves times 1 over 3 halves. I don't like that. We're going to fix it. Plus constant. So when you have one of these with a fraction, really you just reciprocal, take the reciprocal of the fraction. So I'm going to get 2/3 x to the 3 halves plus some constancy. you'll find your own way to solve these. That's how I like to tackle them. Um, Practice and you'll get more comfortable. Hi, kitty cat. All right, my cat is going to come say hi to everybody. Okay, this next one, there's more. We're not at the end yet. This one's pretty straightforward. All right, so I don't have to rewrite anything. I'm going to add 1 to my exponent. So 4 plus 1 is 5 times 1/5 minus, oh, no, we're good. 5x, add 1, gives me 3 times 1/3 plus x, add 1 is 2 times 1/2 plus c, Moby, equals 3/5 x to the 5th minus 5/3 x to the 3 plus 1/2 x squared, some constant c. Sorry, he's going to sing the song of his people for a few minutes. Okay, and again, we can eyeball this, and yeah, it's going to turn back into our original function, which is good if we were to take the derivative. All right, is this my last weird one? Yeah. Okay. There's probably a different way to tackle this, but the easiest one is to do a lot of legwork in the beginning, and then once we actually do the calculus, it comes really a lot easier that way, a lot more straightforward. All right, so we have one thing on the denominator. We can separate this out. I'm going to rewrite this a couple stages. Thanks, Mobs. Yep. I should put parentheses. I never do. Okay. This, no, sorry. Just kind of keep going. Wow, really? Okay. I'm gonna leave off the parentheses. Okay. Hey, where are you going? All right. So this is an understood 1. So I'm going to clean this up one more step. 1 minus 1/2 gives me x to the 1/2 minus, bring my 1/2 up, I get x to the negative half dx. Come on, hop up. Yep, stop yelling. Okay, bye. Sorry, it's his yelling time update. Okay, now we have the same sort of problem we've had. So I add 1 to my exponent. 1/2 plus 1 is 3/2. So I get 2/3 x to the 3/2 minus, add 1 to negative half, I get positive half. So I get 2 x to the 1/2 plus my constant c. Yep, that'll be good. As you go, you won't have to write your fractions after. You'll get more comfortable with that. All right. Yep. We have 2 problems left. So for our particular solutions, we're going to be given a point on our original function, like the one we're trying to find, and we're going to use that to find our c value. So I'm not going to use this piece until my very last step. So really, I get 2x minus 2 dx. Find the antiderivative, x squared minus 2x plus some constant c. So this tells me f of x equals x squared minus 2x plus c. Now I plug in my values. So f of 1 equals 1 squared minus 2 times 1 plus c. And we're told this whole thing equals 2. We can kind of ignore this now. Solve for c. 1 minus 2 plus c equals 2. Gives me -1, so c equals 3. Yeah. Then I rewrite my function. So now we can graph our original function. We know exactly what it is since we were given a starting value. Initial conditions is actually what it's often called. So we're done. We know what that is. All right, next one. X plus 2 dx. 2x squared plus 2x plus c. Yep, that looks right. And f of 1, it's not always 1, that's just the problems I found in the book. Okay, oh, this is interesting. So I get 4 plus 2 plus c equals 8. That tells me c equals 2. Rewrite my function. F of x equals 2x squared plus 2x plus 2. And that's that. These problems can be tricky because you have to think on a couple levels. So write out as many steps as you can. Your goal is to make your original functions as simple as you can. So what you're taking the antiderivative of. You want as many little terms as you can. You want as few fractions as possible. Just simplify them a lot. The next section, we're going to build on this. We're going to do something called a U substitution, which is a really powerful technique. We've kind of skirted around the issue here, but it's very helpful. So I will leave you there and see you next time.